I'm Jennifer Neville, and I'll do the overview for our session in the afternoon, which we loosely called clustering. So we have these four great speakers. Peter Bickel here from UC Berkeley, Andrea Montanari from Stanford, Carl Rowe from University of Wisconsin-Madison, and Vahab Mirakni, who's from Google, who was asking the Google-type questions this morning. So I have a little bit more formality than Michael for the overview, but I should warn you, I'm not a clustering person. So what I thought would be good to do would be to give you just a general sense of the dimensions on which the people that are working on clustering and networks, how they're the kinds of questions that they ask and how they formulate the modeling and the algorithmic approaches to their problem, how they differ, so that you have some context to think about the talks that we'll be having this afternoon, and hopefully that will facilitate some questions that we can have afterwards. So I originally thought I'd give you some sort of basic introduction to clustering work, but we already heard about some earlier in the day, and there's some introductions in the talks this afternoon. So I'll just say there's a large body of work, a lot of people working on identifying communities or clusters or groups and networks, which ranges from people that work on spectral clustering. We heard about modularity maximization and Mark Newman's work this morning, and also stochastic block models. And of course, there's a lot more. And here are, from looking over the talks that are going to be given after I finish speaking, here are some dimensions on which people differ in terms of how they approach this clustering problem, whether they're from the statistics community or the computer science, machine learning community, or whether they're focused on scaling to very large data sets, or if they're more theoretical computer scientists. So first and foremost, how people formulate their problem definition is maybe the first way that they sort of frame how they're going to approach this problem of clustering. And obviously, how to define what is a cluster is a hard problem that exists not even, in the networks community, but in the people that look at data at large. So then certain types of work differ based on the kind of data assumptions they make about the underlying model of the data, and we talked about that a little bit this morning. There's modeling assumptions that people make that may be different from these data assumptions based on how they're going to algorithmically estimate their models, how the models are evaluated, or in terms of accuracy or the properties of the models. That's another dimension. And finally, what people care about in terms of scaling or asymptotics, that differs as well. So just a few quick comments on each of these dimensions. Today, in the talks, we're going to hear both about people that look for global clusterings of the entire network into either distinct partitions, so we want to have separate groups of the nodes where each node only belongs to a single group, or we might want overlapping clusters where nodes can belong to more than one group. And then we're also going to hear several talks that focus at least somewhat on local clustering, because if you think about clustering all of the data into groups, that might not be feasible if you have a really large data set. Maybe first of all, in terms of algorithmically, you might not want to spend enough time to cluster a graph with 1 billion vertices, but also the groups might not make sense if you consider the entire structure. So in terms of the data assumptions, I guess because I'm a person that works more on predictive modeling, I always think about learning a model that's going to generalize to some new data that we haven't seen before. But the interesting thing about clustering, and particularly in networks, is that it's really more of a descriptive task where we want to model the data that we have and describe the data that we see. And so we don't necessarily care about generalizing to new data that we haven't seen, but we want to talk about the properties of the algorithms or the types of clusters we see under some assumptions about what the data have actually been generated from. And so this relates to the topics that we talked about earlier in the day, because we might think about analyzing clustering methods by assuming that the data was generated from some underlying parametric model, and then if that actually holds, what can we say about the kinds of things that our algorithms were produced? Other times we try to make fewer assumptions about the data, but we might give some kind of bounds on the performance of the algorithms where some part of the bound includes some characteristic of the graph, for example, the conductance of the graph. In terms of modeling assumptions, first, if people approach this from a more parametric model-based framework, then what assumptions we make about the characteristics of the models might influence the performance of the algorithm. And we heard a little bit of talk about that this morning in the difference between considering smooth functions versus non-smooth functions for these Bernoulli random variables that would generate the edges. The dimension on which the talks we're going to hear today mostly differ, I think, really can be sort of ground out in our choice of the objective function that we maximize in our algorithms. And so some examples of objective functions are the modularity function that was mentioned earlier. We could talk about cuts or conductance, but also the likelihood of the data. And the choice of the objective function is often sort of intimately tied to our problem definition, because if we say that we want to have groups of nodes such that they have a lot of links inside their clusters and few links outside their clusters, then naturally the way that we could formulate that quantitatively is by considering the cuts between the clusters. Okay? And then in terms of evaluation, there's two major dimensions that I saw in people's talks for today. And one talks more about the correctness or consistency of the algorithms, so that in some cases with some assumptions about the data, we want to guarantee that the algorithm is going to find and return the correct clusters to us. Or maybe to have some sort of bound on the approximation quality of the output clusters under the assumption that there exists a cluster in the data. Okay? And so that's more on the properties of the kinds of output clusters that we get, but also of concern is really the efficiency of the algorithms. And so we might want to have some kind of guarantees that the algorithm is going to scale linearly or log linearly with the size of the data. Or we'll hear with some of the people that talk about local clustering, maybe to have a more efficient algorithm, we want to talk about having that scale linearly in the size of the clusters, local clusters that we find, rather than the size of the overall graph. And something that I think is a sort of tricky subject with respect to clustering, and I didn't see a lot in people's slides when I was looking through them for today, so hopefully maybe we can talk about this more in the discussion, but really there's not a lot of work on validation of these clusters in terms of whether they mean what we hope they should mean about the data. So are the groups or communities, are they meaningful? We tend to have this circular kind of argument that we sort of formulate the problem quantitatively, saying we want lots of links inside the cluster, few links outside the cluster. Then we frame that in a quantitative objective function. Then we apply our algorithm, and then we measure how well did we match that objective function. And so we have sort of a circular type of evaluation normally, and really practitioners, I think, really would care more about, are these clusters meaningful and are these communities sort of important things in the data that we have, particularly when they apply to people or social networks. Okay, and so the last dimension was really scaling or asymptotics. I think there's an interesting difference between the algorithmic computer scientists that talk about asymptotics in terms of runtime and how fast the algorithm is going to grow, and the statisticians that think more about asymptotics in terms of thinking about the estimation behavior of the algorithm. And so I'd like to see a little bit more discussion about, are these orthogonal to each other, or are there interactions between these two? Typically, I myself, if I have my statistician hat on, I say I don't really care about the scaling to the really large graphs, because I really want to understand the properties of how the statistical estimation works. And then later on, once we understand it, we'll figure out how to make it linear or log linear so it'll scale to really large graphs. So that's all I have to say about the overview. I would say that the talks we'll hear will highlight sort of different frames of reference in terms of these perspectives, and then we can sort of consider this further as we talk about it in the discussion afterwards. So I will stop there and pass it on to Peter Bickle, who will be our first talk.